Hi guys, in today's video we're going to be taking a look at Newton's law of gravitation in its full form. So we have dealt previously with the force of gravity near the surface of the Earth, but today we're sort of going to look at a generalized view of gravitation. So if we have any two objects with any mass in space, let's call this object A and this one object B, they will in general be separated by some distance r. And so our gravitational force, the magnitude, will be equal to a big G, which is just some constant that we're given, and this is just Newton's law of gravitation, times both of their masses and divided by this distance separation squared. So this is sort of our law of gravitation, and these gravity forces will be acting towards each other. So that's to say A is attracted to B and B is attracted to A. So this is sort of in general what the law of gravitation is. And so this is the form we'll be using today, and this is the more general form. So when we dealt with the force of gravity on objects near the Earth's surface, it looked a little bit different than this. And the reason is there, we were sort of assuming that the Earth is so big that these objects are very, very small in comparison. And therefore, the radius of the Earth is so much bigger than any variations around the surface of the Earth that this ball or this object or whatever you're looking at may have, such that this distance separation squared is really essentially constant. And so that means that this G, the mass of the Earth, and the separation are all constant, and so those all give us G. So therefore our value of G that we were using was essentially just this right here, r squared. This is the radius of the Earth. And so this was essentially constant, so we then see we have mass of the object times gravity, which is what we dealt with before. So this is again our more general form. And so now that we've generalized our force, we also want to generalize our potential energy term. And that is going to generalize as minus G times MA times MB all over R. And so I'm going to box this because we'll use this today as well. And the one thing to note here is we have a negative sign now. So be very careful. This is a negative potential energy. And the reason is because we want to define the potential energy when the objects are infinitely far apart to be equal to 0. So that's a reasonable definition. And we'll recall that with potential energy, the only thing we're actually worried about physically is changes in potential energy. So we can, and actually have in the past, set our potential energy to be 0 wherever we want, wherever it seems most convenient. And so we're going to go ahead and define 0 potential energy to be when the objects are infinitely far apart. And if that's the case, we know as soon as you bring the objects closer together, their potential energy should decrease. So we see that when they're far apart, that should be the maximum, and therefore this potential energy should just always be negative. It'll never be positive. And so this is sort of the form of our potential energy. We have our force and our energy generalized. So let's go ahead and see how we can use that in today's problem. Two identical stars with mass big M orbit around their center of mass. Each orbit is circular and has radius r, so that the two stars are always on opposite sides of the circle. Find the gravitational force of one star on the other, and find the orbital speed of each star and the period of the orbit. And then part C, it asks how much energy would be required to separate the two stars to infinity. At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have our scenario drawn out over here, and so we see that star A and star B are orbiting the center of mass of the system. So we're told that they're always also opposite on the circle, so that means that their center of mass will just be the center of this circle, and so there will be sort of a radius vector which will point out to here. And then the other thing we're told is there are circular orbits, and so we see then, of course, for star A, if it has a circular orbit about its center of mass, that will just be this dotted line. And of course, star B is going to follow really that same orbit here. And so our orbit is not particularly complicated. These are both sort of just going to be orbiting around the circle. We're told they're always opposite each other as well. So this is what that'll look like, and they're both going to orbit around this dotted line. So for part A, we are asked to look for the force of gravitation of one star on the other. So I'm going to go ahead and focus on star A. They both have the same mass, so everything will really be the same for both of them here. And so for question A, we see if we draw our free body diagram on star A, we are going to basically just get that this has some force of gravitation which will pull it towards star B. And so we can calculate that from before. We know our form is just that this is going to be big G times m of star A, which we see is the same as mass of star B. So this will basically just be mass times mass over, and in this case we see our distance of separation is really 2 times the radius, and then this distance is squared. So we can go ahead and solve. We see the m's become m squared, and this will become 4r squared. So this here is going to be our answer for part A. This will be the gravitational force acting on each star. So for part B, we are similarly asked, now we want to know the velocity, I believe, and we also want to know the period of rotation of this orbit. So for the velocity of the orbit, we can go ahead and see what is causing the circular motion. And so again, from our same free body diagram up here, we only have one force acting on each star, and that's the gravitational force. It clearly is acting towards the center of this circle. So that is to say that our radial force must just be that gravitational force. So we can go ahead and say F radial is equal to Fg. So that is going to give us that what we have as our gravitational force, G times m squared all over 4r squared, must also give us our circular motion condition. So that would be mv squared all over r. And so what we can do here is we see that we know our masses and our radius, or we're told that we know them, and therefore we can just solve this velocity in terms of the mass and the radius. And so what we should then get is our velocity should be the square root of gm all over 4r. And so again, I will now box this here. So this is our velocity term. That's to say the velocity, the tangential velocity of each planet is given by this. And so similarly, we can now solve for our period. So I'll go ahead and move over here. And we know simply that the velocity is going to be equal to the distance traveled, which will be the circumference of the circular orbit, divided by the time it takes, which will be the period, the time it takes for it to complete one orbit. So therefore, we can go ahead and rearrange this, plug that in, and solve, and we should basically get the period is going to be, 2 pi r times the velocity, which is square root of gm over 4r. So there's our period as well. And so now what we want to do is we want to look for part C, which asks us about the energy it would require to move these stars, to separate them out to infinity. So we want to start out by what do we know when these stars are separated an infinite distance. And our first thing we know is that, of course, the potential that we have defined at infinity, so potential at infinity is equal to 0. And again, this is by definition. Talked about this at the beginning of the video. And then similarly, let's say that we've just separated the stars out to infinity and there's no more motion. So also the kinetic energy at infinity will be 0. So really their total mechanical energy once we're out at an infinite separation is going to be given as 0. So what we can now do is we can recall we have a relationship between work and between mechanical energy. So if you remember from that section, we basically have that the mechanical energy initial, so that would be U initial plus kinetic energy initial. That's our initial mechanical energy. We can add our work, which will basically give us a term which tells us the change in mechanical energy, should give us our total final mechanical energy. So make sure you recall this relationship. You see where this comes from. And once we have this, we can just note this work term is really just what we're looking for. This is the amount of energy that it's required to separate these stars a distance to infinity. So we can go ahead and rearrange this, and we'll see that the work is equal to the final mechanical energy, which we know is 0, right? So we can go ahead and cross this out. We know final U is U at infinity. Final kinetic energy is kinetic energy at infinity. So really, we just get work should be negative UI plus kinetic energy initial. And so at this point, we really just have two terms we need to solve for. So our kinetic energy initial is going to be just as usual. This is going to be equal to, let's see, I'll do this over here. This will be equal to 1/2 mv squared for each of these. So it's really 2 times 1/2 times the mass, which is just big M for each of them, times V squared. So that would be gm over 4r. The square will get rid of the square root here. So we have that as our kinetic energy term, and now we can recall the form of our potential energy, and that is just to say the potential energy is minus gm squared all over r, right? This is minus gm times m over r. So we can plug that in down here, and we get minus gm squared over r. And at this point we can solve this, and this gives us the energy required. And we will see that we should finally get to a form of g times m squared all over 4r. So that's to say we need to put in a total amount of energy of gm squared over 4r in order to separate these stars to infinity. Okay, so let's recall what we've done here. We first solved Newton's law of gravitation directly to find the gravitational force of one star on the other. Then we saw that this gravitational force was our radial force and solved the condition for uniform circular motion. We then used this to solve for the period as well. And finally, we utilized the relationship between mechanical energy and work to solve for the required energy to separate these stars to infinity. Okay, so I hope this video was helpful, and I hope you get some sort of idea of how to apply the more general form of the force of gravitation and the potential. So if you have any comments on this video or any of the videos, please leave those in the comments link, which should be to the right of the videos link. Thanks for watching.